Gravity feels familiar. It pulls objects downward, keeps planets in orbit, and gives weight to everything around us. From everyday experience, gravity seems like a simple force acting at a distance, one that pulls masses toward each other in a predictable way. For centuries, this intuition worked remarkably well. Classical physics described gravity as a force that acts instantly across space. According to this view, Earth pulls the Moon, the Sun pulls the planets, and objects fall because a force acts on them. But modern physics tells a very different story. Gravity is not a force in the usual sense. Instead, gravity is a consequence of how mass and energy shape the structure of space and time themselves. This idea changes how we understand motion, weight, and even the shape of the universe. To see why this matters, consider a simple situation. When you drop an object, it accelerates toward the ground. We naturally say that gravity pulls it downward. But this description hides something deeper. In modern physics, objects in free fall are not being pulled at all. They are moving along the straightest possible paths through curved spacetime. What we perceive as a gravitational force is actually the result of space and time being distorted. This is a radical shift in perspective. Instead of asking why gravity pulls objects, physics asks how mass changes the geometry of reality. Massive objects like planets and stars bend spacetime around them, and other objects simply follow the paths created by that curvature. This explains a remarkable fact. Astronauts in orbit around Earth feel weightless, even though Earth's gravity is still present. They are not outside gravity. They are freely falling through curved spacetime. From their perspective, no force is acting on them. They are moving naturally, following the geometry of spacetime shaped by Earth's mass. This idea also explains why gravity affects light. Light has no mass, so a traditional force-based view of gravity struggles to explain why light should bend near massive objects. But if gravity is curvature, the explanation becomes clear. Light follows the shape of spacetime just like everything else. When light passes near a massive object, its path curves because spacetime itself is curved. This effect has been measured and confirmed many times, from eclipses to modern astronomical observations. Gravity does not pull light. Spacetime guides it. This geometric view of gravity has profound consequences. It explains why gravity is not instantaneous. Changes in the gravitational field propagate at the speed of light, not infinitely fast. When massive objects move, they create ripples in spacetime known as gravitational waves. These waves carry information about violent cosmic events, such as merging black holes or neutron stars. Gravitational waves were predicted long before they were observed. When they were finally detected, they confirmed that gravity is not a force transmitted through space, but a dynamic feature of space-time itself. This also changes how we think about weight. When you stand on the ground, you feel heavy not because gravity is pulling you downward, but because the ground prevents you from following your natural path through space-time. The force you feel is the resistance of the ground pushing you upward. In free fall, that resistance disappears. That is why falling feels weightless, even though gravity is fully present. This perspective reverses the usual explanation. Weight is not caused by gravity acting on you. Weight is caused by something stopping you from falling.
Understanding gravity as geometry also reshapes our view of the universe. On the largest scales,
Gravity determines how galaxies form, how clusters evolve, and how the universe expands. The distribution of mass and energy shapes spacetime, and spacetime guides the motion of matter in return. This interplay between geometry and motion governs cosmic structure. It explains why galaxies rotate the way they do, and why the universe has the large-scale patterns we observe. Gravity is not just an interaction. It is the architecture of the universe. This view also places limits on what gravity can do. Because gravity is geometry, it cannot be shielded or turned off. Space-time always responds to mass and energy. At extreme densities, space-time curvature becomes so strong that even light cannot escape. These regions are what we call black holes. Near such objects, gravity does not pull harder in the usual sense. Instead, space-time becomes so curved that all possible paths lead inward. Time itself slows down near strong gravitational fields. As gravity increases, the flow of time changes, linking gravity directly to time. This is why gravity, space, and time cannot be treated separately. They form a single, connected system. Gravity is not a force acting within space-time. Gravity is space-time acting. Once you understand this, gravity stops being a mysterious pull and becomes a structural feature of reality. Objects move the way they do not because they are forced to, but because space-time itself tells them how to move. Gravity is not a force, it is geometry, and that changes everything. Next, we'll explore what happens when this geometry collapses completely, inside a black hole.
If this helped, hit like and subscribe for one 10-minute idea every day.